Okay, we were looking at exponential functions. We looked at what logarithms are and some of the basics about logarithms and how they're related to exponentials. We're going to keep looking at that to some degree here, but today we're going to focus on graphing logarithmic functions. And it's a little bit of a challenge to come up with points that are actually useful to graph. So we're going to practice graphing some. We're also going to look at some properties of logarithms that, as long as you keep in mind the fact that logarithms are exponents, they're not too hard to remember these rules, okay? And I'm actually summarizing two different boxes in your book, okay? There's properties of logarithms and then properties of natural logarithms. And to be honest with you, I'm not really sure why your book has two separate boxes for this, because
they're very similar.
What are natural logarithms?
Logarithms.
Base 10.
That's the common log.
Base E.
Base E, okay? So, if it's a logarithm, all of this will still apply, right?
Are they literally exactly the same?
They are, except these use e's and natural logs, okay? So let's look at them, alright? You can see the similarity. First of all, the log base a of 1 equals 0. Or the natural log of 1 equals 0. Remember, what a log equals is the exponent of the base. So here we have something to what power would give me 1? Well, anything to the 0 power equals 1. Okay? Except for 0, but you can't have a log base 0 anyway, so that doesn't matter here. Okay? And that also applies for e. E to the 0 equals 1, so the natural log of 1 is 0. Okay? So that's our first property. If you have a log base anything of 1, it's always going to equal 0. Okay? Secondly, the log base a of a equals 1. What exponent of a will give me a?
1.
1. Because anything to the first is itself. Okay? And again, that still applies to e. E to the first is e.
So tricky.
Okay? Our third one. These aren't real difficult as long as you remember these are exponents, okay? Our third one. This one we've kind of used, and this one recognizes the inverse property, okay? The log base a of a to the x equals the x. Remember we said a log and an exponential with the same base are inverses of each other. So log base a of a to the x equals x. The other side of that, and this just finishes out the whole concept of the inverse, if we have a, an exponential, with the logarithm in the exponent, a to the log base a of x power, that gives us x. Now, you will probably never see this.
You saw it on a scope and
Second one. Okay?
They're the same.
They're very rare. I'll tell you that. Okay? But if you're thinking an exponential and a logarithm with the same base, if it's in a combination where you have the log of the exponential or an exponential with the log in the exponent, either way they're going to cancel each other out. They're inverses.
It was just like so hard.
You'll be left with just x.
They're the same.
Okay?
I think we should went over.
What?
They're the same.
It's hard to like
It gives you just x. Okay? Notice here, what does an inverse do? It does the opposite of what its inverse does, okay? Or what the function does. So here, think of your order of operations. Here, you would have to raise a to the x power, then the logarithm takes you back to x, right? Here, you're taking the logarithm first, then the exponential takes you back to x. Alright, either way, you're starting with x, you end with x because they're inverses. Okay? The last one here, you might look at it and just think, well, duh, of course that's true. But really, the last one here, it's what's called a one-to-one property, and that's what makes the inverse not just an inverse, but an inverse function. Remember, we had that term one-to-one before. Okay? The inverse function is because if you take the log, if two logs are equal and their bases are equal, then what you're taking the log of has to be equal. Okay? And just to kind of illustrate that, if I have the log base 5 of x, and that's equal to the log base 5 of 3, then x has to be 3. Okay? There's not going to be any other value that I could plug in that'll give me the same value as log base 5 of 3. X has to be 3. Okay? Does that make sense to everybody? Okay? Alright. Now again, this isn't anything super difficult, it's just a matter of thinking in terms of your logarithms. We'll see how you can actually use this later on as we start to solve equations tomorrow. Okay? We're going to be able to solve equations. Well, actually, we don't get to that point tomorrow. We'll get to that point later on this week. But tomorrow we'll start the process to work where we can use this pretty well. Okay? Now, let's think through how we would graph this. F of x equals the log of x. Okay? One of the things that might be helpful is to kind of turn around in your mind the way you typically find points. Okay? Typically, when you find points and you have no idea how to graph something, you'll just pick some number for x, plug it in, and see what comes out, right? Alright? Well, here we're going to kind of turn that idea backwards in our heads. Alright? You guys know that if f of x is log of x, that means x equals what? 10 to, where'd that go? Oh, I must have bumped it. 10 to the f of x power, or y, if you want. Okay? So in this case, it's actually easier to plug in different values for y and then see what the x would have to be. Just make sure you graph it properly when you do it. Okay? So, let's say I wanted y to be 0. I'm getting an x-intercept in this case. It would be 1, okay? 10 to the 0 power is 1, so that gives me the point 1, 0. Okay? Here's x, here's f of x. I got the point 1, 0. Okay? Now, let's say I want x to be 1. Or I'm sorry, I want f of x to be 1. Then I would have 10. Okay? If this is 1, then this is going to be 10. So when x is 10, I'm here at 1. Alright? What if I want f of x to be 2? What does x have to be? 100. Okay, now, obviously that's way off of our graph, but that should show us, we're not going to get up to 2 until way over here at 100. Okay? So this is not going to increase very much. Alright? So, this side of the graph looks like this. Okay? Any questions?
Doesn't it also, never mind, different function. Sorry.
Okay.
Looks like our receiver.
Now,
Looks like the other one.
x could also be negative, right? Or I'm sorry, f of x could also be negative. What if I wanted f of x to be -1?
One time.
That would give me, yeah, 1/10. And -2 would give me
Yeah, to 100.
1/100. Okay? So you can see here,
Get the other one.
alright, what do I have?
How do you make x 0?
An asymptote.
An asymptote, okay? We have an asymptote here at x equals 0 because no matter what I plug in, 10 to any power will never equal 0. It'll approach 0 because as that 10 to whatever gets bigger and bigger, I'm going to have 1 over something huge. And that'll be really close to 0, but it'll never actually equal 0. Okay? So, that's what the graph of log of x with a base of 10 would look like. Okay? Now,
Wait, so what? The asymptote's at x equals 0? I thought it'd be y.
no, it's not equal 0.
X?
Yeah. Y equals 0 is when you did the exponential. You had a asymptote at y equals 0.
Yeah, that makes sense.
Yeah. And we'll see that again in a few minutes here. Find some points to graph this one, okay? This one is a little bit, we have a base of 2, so you'll get a little bit smaller numbers, okay? Let's find a couple of points. Someone give me 1 point.
One.
That's not a point.
Get it together.
Which one you are?
Get it together.
2 comma
Are
1.
you okay?
What is it?
2 comma 1.
Okay, if g of x is 1, because remember this says x is going to equal 2 to the g of x power, right? Rewriting it like that can be helpful. By the way, remember on the homework from Thursday, you were rewriting logarithms as exponentials and exponentials as logarithms?
Yeah.
This is why, okay? Helps you think through that. So we have the 0.21. Good.
4, 2.
4, 2,
8, 3.
8, 3.
1, 0.
Okay. 1, 0. Good.
1/2 -1.
All right. Let me get some of these on here. All right. Here's 4, 2, 8, 3, 1, 0, and you said 1/2
1/2.
-1.
Yeah.
Okay. Good.
1/4. Yeah, 2.
Wait. 1/2. That's the -1.
128
All right. 1/2 -1. There we go. Okay. And that's right. Okay, you can keep going up. When are we going to hit 4? At 2 to the 4th. Well, that's 16. When are we going to hit 5? At 2 to the 5th power. That's 32. Okay? And that's as far as our graph's going to take us. But here you have 1/2 -1. We'd have 1/4 -2. 1/8 -3. 1/16 -4. Okay? So you see, again, you have that asymptote at x equals 0, and then this comes over here like that. But we won't hit 6 until we get to 36. Okay? Or not, 64, sorry. 64.
Do you ever have horizontal asymptote?
Well, let's think about this one. Do we have a horizontal asymptote here?
No.
No, because it's going up slowly, right? But it will continue to go up forever.
But could you ever have one?
Not with just a plain logarithm like this. Yes.
Is there any way to algebraically figure out what your weight loss interval will be, or you just have to like plug in?
Well, algebraically, you'd be solving this equation. 0 equals 2 to the y power. 2 to what power will give you 0? Nothing. Okay? So there is a little bit of logic. It's a little bit more logic than it is algebra, but yeah. And also, it can't be negative. If you have a positive 2, no matter what power you raise it to, you're never going to get a negative. Okay? So, let's kind of summarize here, and then we will take a step back. Oh. I don't know why they got dragged down there. And then we'll summarize some things. Okay? Here's the basic look at the graph of log base A of x. Alright? A has to be a positive number bigger than 1. Okay, we're not going to do log base 1/2, although that's mathematically possible. We're not going to graph, log base -2. Alright, while that's mathematically possible, that doesn't have a graph that follows any of these rules. Okay, but this is the basic look of the log base A of x. And let's look at a couple of things related to it. Okay, first of all, the domain. The domain, what x can be, x is always going to be greater than 0. Okay. Our range. The range, the function value, is going to go from negative infinity to positive infinity. It approaches negative infinity as x approaches 0. Okay? It approaches positive infinity as x approaches infinity. Okay? Notice, too, it's always increasing throughout the domain. Okay? It doesn't have a max point, a local max point. Alright? And if we did cut it off into an interval, whatever the end of that interval was would be the max point because it's constantly increasing. Okay? That's the only way we could get a max point is to get some interval. But let's look right here. Okay? The reflection of the graph of f of x equals a to the x in the line y equals x. Okay? What did we get when we reflected a line across the line, or we reflected something across the line y equals x?
The inverse.
We got the inverse, okay? And because we had that one-to-one function, or that one-to-one property, we know it's an inverse function. Okay? So guys, let's take a step back for a moment to this one. Here's that line y equals x, okay? It went through here, through the origin. Here's the line y equals x. Let's think about the reflection here. Let's do this. What would the inverse of g be?
G to -1.
Yes, but what would that be?
Log 2 of y.
Okay. X would equal the log base 2 of y. How would you solve that for y? Y would equal,
Well, it'd be 2 to the x equals y.
very good, 2 to the x power. So our inverse is 2 to the x power.
Oh.
Okay?
Well, when the log is, well, okay. So, is the inverse whatever function you're looking for, or is it like the function is always the inverse of the...
They're inverses of each other, so whichever one you start with,
You call the other one the inverse?
you call the other one the inverse, yeah. In this case, we started with the log base 2, so the inverse would be 2 to the x. Okay? Now, you guys already learned how to graph this. It always goes through the point 0, 1. I have other points 1, 2, 2, 4, 3, 8, 4, 16, 5, 25.
-1 1/2.
Okay, yeah, -1 1/2, -2 1/4, -3 1/8, and so on.
128.
Well, look at this. You're going into programming that 2 to the 8th equals 128 will be important. Okay. Or actually, no, 2 to the 7th is 128. 2 to the 8th is 256. Because an 8-bit, there are 8 bits in a byte, and a byte can go from 0 to 255, so 256 characters. So,
268.
what? That's 2 to the 8th power.
Yeah, I know.
Anyways, notice though, look at the graph. Look at the graph. We've got a reflection here. A reflection across the line y equals x. Okay? So, you notice here our logarithm had an asymptote at x equals 0. We knew from before our exponential, even though I kind of have it going up a little bit there, our exponential has an asymptote at y equals 0. The domain here is everything greater than 0. The range here was everything greater than 0. Look. So, make sure you remember what we have done before, okay? Relate our exponentials to our logarithms, okay? And remember that for an inverse, they simply swap intervals. The domain of one function is the range of the other function. And the range of the first one, the range of our logarithm is all real numbers. What was the domain of our exponential? That was our range. The domain of our exponential was all real numbers. Okay? So keep that in mind. Inverses swap their domain and range. Okay? Are there any questions? Okay. All right. You want to try one more?
Yeah.
Try one on your own. All right. Let's do this. Let's do a different one. Let's kind of put it all together. Get rid of that. Well, we'll leave that there. We'll get rid of that though. Okay? Let's say that we have f of x equals the log base 3 of x. Okay? So, couple things. First of all, try graphing it. Secondly, find f inverse. And thirdly, graph f inverse. Okay? And go ahead and pull up next to someone next to you. You can work together
No.
to find some points.
Okay.
Wait,
Don't all move at once.
Is that 3 under the log? The base is 3?
Yes, the base is 3. Sorry, it's a little squiggly.
Thank you.
Okay? And don't just reflect it. Actually find the points and make sure it actually ends up being the reflection. That's how you check yourself.
When it says find f
Your imaginary friend.
Yeah.
when it says find f -1 is not it's right equation, right?
Yeah, find what that function would be, f inverse.
no friends can say that someone else is
He's Portugal work with you, just so you know.
No. What? No, y'all pulled me over here.
Yeah, no other option.
Nah, I got it, yeah.
Alright, let's do this.
What are you doing?
You guys are graph.
You guys are
Oh,
Yep.
You drink your status.
No way.
No,
That's
that's
right.
right.
It
So cute.
actually does keep your teeth from getting stained. If you drink from a straw.
You guys don't even have graph
Teaching
paper.
life skills
Your
as well as
dental hygiene fact of the day.
There's the
You don't even need it.
Yeah.
Oh my
Some people are dumb.
You know you're a good friend.
Graph
It's
paper.
okay, it's not a race.
Shit.
It is a race.
I got
Draw the,
Make it a race to be right, not necessarily a race to be done.
Nah.
Yeah, but Jacob's done, so.
Take a bit done.
Already?
1, 0,
I'm offended by that.
2,
No.
2, 8.
Chickens are done. You are
Coordinates,
finished.
guys.
Drop acid, not war.
Don't just automatically erase it, you know what you did?
Yes, I switched my.
There you go.
Alright.
And I'm not erasing it, I'm waiting it out.
Waiting it down.
Let me help me. I don't feel like finding this.
That's why you use pencil.
27,
Dude, it's
3.
so soft being information so you're so bad at math.
You
What's
did
three
it,
to
you
the-
did it
what's
too.
three to
Did I?
zero?
Yes.
Did I?
So then why were you saying it differently?
I wasn't saying it differently.
Yes, you
Just
were
what
saying
you were
it.
copying.
No, I didn't.
Just count.
So you know what you're doing now?
Yeah.
Yeah, just need to copy my points.
I feel so dumb.
Wait, you already finished all of them?
Yeah.
1/3 is -1.
What's three to the negative?
You wanna, Lexi, you wanna break my hair?
You were on the right track.
Tell me why I would be
Swap.
Give me math.
Why are you being
Okay.
mean today?
Okay, yes. So,
Is it inverse?
well, when you do the inverse, which, to do the inverse,
Even though
and this was chapter 1, so this is before you joined us,
My head
okay?
goes.
You switch the x and y coordinates, so it would be,
now I got
well, if you go back to the beginning, x equals the log base 3 of y. So then to solve for y, you translate it into an exponential like this, but now it's y equals 3 to the x, okay?
I know.
And again, it goes back to what we were looking at earlier, the logarithm and the exponential at the same base are inverses of each other. So here you have a base of 3, so what's the exponential with the
I
base
know,
of 3?
same.
Does it come like seeing you guys on?
He's a nice person. He's just very selfish. Oh, for sure. He's never listened.
Alright, doesn't have to be,
Shout
this
out.
is an art class, so.
Do this.
When you graph it, make sure you get the other half, like going towards that asymptote and this one
Yeah.
towards the asymptote. Do you have a question, Lexi?
Are you ready?
Oh, yeah. No, that's good, that, I mean, that's fine, that's good.
Yeah, you're fine.
And then. Alright, how are we coming? We have them graphed?
Almost.
Almost? Almost?
Mr. Hickson, how do you define,
Oh, well, remember, what's the inverse of a logarithm?
They were all fat.
and.
No, the other tab.
No, that's just a log with a base of 8.
Just see, Lexi. I'm pretty sure Mr. Plenty world project this like that.
See that what we did
So
earlier?
if I like walk in, like,
He's so creepy.
you don't like him?
Okay. That's, that's right.
Good.
Good.
Oh,
Exponential is the same base as the inverse of the logarithm. Okay.
There's no chance I made that up.
Oh yeah. Did you see my Snapchat story?
I'm so mad I'm not actually sorry anymore. Because like, when I was doing this on the sheet, like, I see.
No, it's not going away.
Alrighty, let's real quickly here. Let's come up with some points for f of x. Give me a point for f of x.
1.
0.
0.
It's not a point.
1, 0. Okay.
127 negative 3.
Okay.
9, 2.
9, 2.
27 3.
Okay.
3, 1.
3, 1. Okay. So that gives us a good idea. We'll stick with those for right now. We could also do 3, 27, or I'm sorry, 27, 3. All right. Let's look at that one.
81.
Okay. 1, 0. Here, 2, 9. 2, 9. There we go. No, that's not 2, 9. 2, 9. Sorry. Okay. Oh,
9, 2.
9, 2. I'm all over the place here. There we go. 9, 2. Finally. 27. 1, 2, 3, 4, 5. So that's 27, 3. Okay. And so that's what that's going to look like. 81, 4 would also be a point. Okay. Guys, please cut it out. Alright, so we have that for f of x. Now, let's look at g of x. Okay? Or, I'm sorry, f inverse of x. Okay? So, f inverse of x. Okay?
0, 1.
First of all, what is f inverse of x?
It's the swap.
3 to the power of x.
What? Hang on, Nico?
3 to the power of x.
3 to the power of x. Guys, listen, we did this earlier. The logarithm is the inverse of the exponential with the same base. So, some of you are setting it up in the equation and you're doing log base 3 of y equals x. And yes, algebraically, that's how you can find an inverse. But here it's much easier if you just think about it, okay? The logarithm and the exponential are inverses when they have the same base. So if you have log base 3 of x, the inverse is 3 to the x, okay? Now, what are some points you guys got for that?
0, 1.
0, 1,
2, 9.
1, 3,
9.
So basically you
2, 9,
Change it over.
just come
5, 246.
327, right? Negative 3, 127, Jacob. There you go. So look, what do you notice happened?
Oh, so they just
just
like, the
switched.
point switch.
Yes, you just switch your x and y coordinates. Okay? You see that? There's a reason why I wrote them in the same order. You can see that. Alright, so we've got 0, 1, 1, 3, 2, 9, 3, 27, ends up off the chart here. Okay? And that does end up being the inverse function. Okay? And it's the reflection across that line y equals x. Okay, Yash? Yeah, go ahead. Any questions? Quick questions. Alright, now, in the last 10 minutes here, what I want to do, we've looked a lot at the graph of just the basic logarithm function. Okay? But everything that we've learned about how to transform a parent function still applies. Okay? So think with me. How would I move the log base 3 of x to the right 4 spaces?
Log base 3 of x minus 3.
Plus right 4 spaces.
Right 4 places.
Minus 4.
X log base 3, x minus 3.
Oh, x minus 4.
Okay? Would the x minus 4 be in the parentheses or would the minus 4 be outside?
Inside.
Inside. Okay? If I wanted to shift this thing 4 places to the right, it would be the log base 3 of x minus 4. Okay? And if I wanted to shift it 4 places to the left, it would be x plus 4, right? That's the same thing. What if I wanted to reflect this across the x-axis?
Negative
The same but outside.
What?
Negative log.
Negative log. negative log of 3 log base 3 of x would reflect this across the x-axis. What if I wanted to reflect it across the y-axis?
Negative x inside.
I'd make the x inside negative, and it would reflect it across the y-axis, okay? All that stuff still applies here, okay? If I wanted to stretch it 3 times its normal height, I would have 3 times the log,
Or we just actually x.
okay? What?
It's actually log base 3 of x cubed.
Yeah, and you could convert it to that. We'll be looking at that tomorrow. So, those things tomorrow, that's good. So, the graphs and all that, that's really the only new stuff. All the other transformations are just applying what we learned in the past to what's new here, okay? So, I gave you a couple of problems to work on. These are very similar. These are very similar to the ones I had given you on, it would have been Thursday, where you were writing an exponential as a logarithm, okay? Notice the example here. By the way, what's a cube root? What power of e is that?
3.
Well, can I say?
1/3.
1/3, okay? Remember roots, the index goes in the denominator, okay? So it's the 1/3 power of e, okay? Negatives are like this one, okay? Then you have some graphing. They give you a function, okay? Notice the difference here. If it's not in parentheses, don't assume it's in parentheses, okay? This is log base 3 of x plus 2. This is negative log base 3 of the quantity x plus 2, all right? Pay attention to those parentheses. Okay, so you've got some of those. Some others where here's the original function. What's going on? Describe it in words. Is there a reflection across the x-axis or the y-axis? Are we shifting it up or down or left or right? Okay, write down those. And then here, using your graphing calculator. If you do not yet have a graphing calculator, you must have one. Okay? And here's the thing, you might have been getting away with not having one up till now, but we are doing stuff this year that you will have to have it for, and you've got to learn how to use that thing, okay? If you don't know how to use your calculator, it's not worth anything to you, alright? So even now, while we're still at stuff where you might be able to get away with not using a graphing calculator, get your graphing calculator, use it, learn how it works, how to do things with it, because here's the thing, when it comes time for the test, there are going to be problems you have to do on the calculator. And also, I am not going to take test time to explain to you how to do stuff on the calculator. Alright? If you want help, I'd be happy to help you learn, but not during the test. Okay? So make sure you're getting that, learning how to use it, come to me and ask before or after school or something, or even ask here in class. I'd be happy to help you, okay? One thing about this, it says find open intervals where we're increasing or decreasing, okay? And approximate relative maximum or minimum. How do we find max or min points on our calculators?
Analyze graph.
Analyze graph or above trace. Don't just trace, but do second trace to calculate. If you've got the TI-84 or 83. If you've got the Inspire, you're going to use analyze graph. And you can then find maximum or minimum. You've got to know how to use those basic functions of the calculator. Okay? So, take a look at those. We'll go over those first thing tomorrow.
Can you post that on your blog?
Okay? What?
The CMs, 'cause it was a
Oh, yeah.